Nernst equation. Right. This Nernst equation explains a relationship between electrode potential and concentration of electrolytic solution. Okay. So if you want to write a relationship between electrode potential and concentration of electrolytic solution, we take Nernst equation. So while writing this Nernst equation, first we take an equation. So I take like this: M aqueous solution. It contains some electrons, Mn plus in aqueous form. So here electrons can be gained. By gaining electrons, it can be formed as a metal solid. Okay, it is an off-cell reaction. So here gaining of electron means this off-cell reaction takes place at cathode. Okay, so this reaction takes place at cathode. So generally at cathode, the reaction which takes place, that is called reduction. So it is reduction reaction. So for this reduction reaction, we can write relationship between electrode potential and concentration of electrolytic solution. It is solution form. Okay, so for this reaction, if you can write an Nernst equation, we can take like this. It is E cell. E cell indicate electrode potential. Okay, and it is equal to E naught cell. Here E naught cell indicate standard electrode potential. It is electrode potential, and E naught indicate standard electrode potential. And you see here minus RT by NF ln. Okay, and you take product by reactant. Here the product concentration is, the product is metal, so it is present in solid form, by reactant is in aqueous solution form, so we write like this. Okay, it is a Nernst equation for this off-cell reaction. Okay, in this reaction you see R indicate the gas constant. This constant value generally we taken in joules, that is 8.314 joule mole inverse Kelvin inverse. It is R value. Okay, and when you take temperature, generally we take absolute temperature. So absolute temperature here we taken in kelvins. So this reaction at 25 degrees we have to done. So at 25 degrees means in kelvins we take 298. Okay, and here N indicate number of electron transferred and F indicate Faraday. 1 Faraday is equal to 96,400 coulombs. Okay, so by substituting these values in this, and their ln is present, so whenever you convert ln into log, in the place we take 2.303 log. Okay, by substituting all this in this equation, that equation formula can be converted into like this: E cell is equal E naught cell minus 0.059 by N. Here N indicate number of electron transferred. For different reaction, different number of electrons can be transferred. That's why you take N. And you see, and in this place, total in place of ln we write log, and it is concentration of metal by concentration of solution. Okay, and generally see, whenever concentration we have to taken for metals, it is the value of concentration of metal generally we taken as 1. Okay, that's why in place of this we type 1. Then that Nernst equation can be written as E cell is equal E naught cell minus 0.059 by N log. Now your concentration of metal can be taken as 1. Okay, so by 1 m n plus aqueous. Okay, it is a Nernst equation for this off-cell reaction. Okay, so when you take this Nernst equation for this off-cell reaction at cathode, you can written like this. Okay, that is equation is E cell is equal E naught cell minus 0.059 by N log 1 by concentration of this solution. Okay, so it is a Nernst equation for this reaction. It is takes place at cathode. Cathode means it is reduction reaction. That's why by using this we have to find reduction potential. Okay, and same reaction if you write at anode. Okay, it is at cathode. Whenever you write same reaction at anode, the reaction can be reversed. Now we can see how can you write like this. Okay, if this reaction it is cathode, at cathode E cell is equal E naught cell minus 0.059 by N log, and here product is solid concentration can be taken as 1, and reactant in aqueous solution form to take concentration. Okay, right, now this reaction, now we can write at anode. At anode reverse reaction is takes place. So at anode the reaction of it is present, and what is the relation now we can see. Okay, so if you write the reaction at anode, first you take solid metal in solid form, it can be converted into aqueous form by the releasing of electrons. Okay, so it is an anode. So anode means it is a oxidation reaction. So here the potential find, that is called as oxidation potential. Okay, same reaction you have to take it. So if it is takes place at anode, directly I written E cell is equal E naught cell minus 0.059 by N and log and here you see now it is product. Here we have to write product, so it is the product. So concentration of product means M plus. Okay, right here reactant no need to take because it is solid. Solid concentration can be taken as 0. Okay, so here E cell, if you want to get your potential value, that is oxidation potential, and reverse reaction it is reduction reaction. By using that we get reduction potential. Okay, it is for oxidation reaction. Before equation what you write, it is for oxidation reaction. Okay, so it is a Nernst equation to find electrode potential, and here we get a relation between electrode potential and electrolytic solution. Okay, right, now if you want to write a relation between electrode potential and equilibrium constant, now generally we take an equation like this. You see, E cell is equal E naught cell minus 0.059 by n log, and numerator already we know that the concentration we taken is products concentration, and in the denominator generally we take reactant concentration. Okay, it is a Nernst equation. Okay, so when you apply Nernst equation for a cell reaction, E cell is equal E naught cell minus 0.059 by n log product concentration by reactant concentration. Okay, right now you see, in place of this, E cell is equal E naught cell minus 0.059 by n log, in place of product concentration by reactant concentration we take QC. Okay, here Q indicate reaction quotient. Here reaction quotient it is applied at any condition. So to write about product concentration by reactant concentration, in place of product concentration by reactant concentration we take QC also. C indicate concentration, Q indicate this ratio. Okay, right, it is a general Nernst equation. And when you write at equilibrium, if you take equilibrium condition, at equilibrium condition E cell value can be taken as 0. Okay, at equilibrium electrode potential can be taken as 0, that means it is 0. So this we write this side. Then E naught cell, from that condition E naught cell is remaining, so E naught cell is equal to, then we write like that, minus can be changes into plus 0.059 n by log Kc we written. Okay, that means at equilibrium in place of Q what you take, K we have to take in. Here Kc indicate equilibrium constant at certain constant. Okay, okay, it is equilibrium constant in terms of concentration. That means if you write equilibrium constant in terms of concentration, this we write Kc. Okay, so it is a relation between electrode potential and equilibrium constant. Okay, when you take at equilibrium constant, E cell value can be taken as 0. Okay, so in the problems here equilibrium constant value is given and asking to find about electrode potential, we use this relation. Okay, in this relation again n indicate number of electron transferred within the reaction. How many number of electrons are transferred, that number of electrons we write in the place of n. Okay, so this equation is relation between electrode potential with equilibrium constant. Okay, right, now if you want to write a relation between electrode potential and free energy change, okay, here another relation is present, that is a relationship between electrode potential and free energy change. Generally free energy it is represented with delta G. So delta G is equal minus NF E cell. Okay, it is the relation between free energy and electrode potential. Here N indicate number of electron transfer, F indicate Faraday, and here E cell is electrode potential. Okay, it is normal condition. If you write it standard condition, we can take delta G naught is equal minus NF E naught cell. Okay, it is at standard condition. Standard condition generally temperature take 298 Kelvin. At 25 degrees temperature we have to apply this. So delta G naught is equal minus NF E naught cell. Okay, so it is relation between free energy and electrode potential. Okay, right, now you take this delta G, it is free energy change, or at standard condition delta G naught. Okay, right, now electrode potential E, or at standard condition we take E naught, and your equilibrium constant K or Kc we have to take it. Okay, if you write about these three relations for the reactions, if the reaction is spontaneous, okay, for a spontaneous reaction already we know delta G value is negative. Negative means it is nothing but less than 1. Okay, in the case it is greater than 1, it is also greater than 1. Okay, it is asking in examination, you remember compulsory question is coming from this concept. Okay, for a spontaneous process delta G less than 1, E value greater than 1, K value also greater than 1. Okay, right, similarly if you write for non-spontaneous process, okay, if it is a non-spontaneous process, in that condition it is reverse. That means delta G value is greater than 1, E value less than 1, K value also less than 1. Okay, that means it is negative, positive, positive, and here it is positive, negative, negative. Okay, if these three conditions you applied at equilibrium, okay, if the condition is equilibrium, at that equilibrium condition, delta G 0, E cell 0, K value also 0. Okay, so these information we have to remember. It is important information. Okay, for a spontaneous process, delta G less than 1, E greater than 1, K greater than 1. For non-spontaneous process, delta G greater than 1, E less than 1, K less than 1. Okay, if you apply an equilibrium, all these values can be taken as 0. Okay, right. This information is important. You can remember. Right. After this, now if you write this Nernst equation for hydrogen electrode, okay, so now you can see hydrogen electrode. Right. So hydrogen electrode. Now we can apply Nernst equation for single electrode potential. For that, here we take hydrogen electrode. So hydrogen electrode can be act as cathode as well as anode. So one condition we have to take in here, that is H2. It is in gas form. It can be formed as 2H plus in aqueous form, and here electrons can be released. 2 electrons. Okay. So releasing of electrons means this reaction takes place at anode. Okay. This reaction at anode. Anode means the potential it is called oxidation potential, because here the reaction is oxidation reaction. So oxidation reaction means at that case you want to find oxidation potential of hydrogen electrode. How can you find? We have to see here. Okay, so you applied the Nernst equation for this. It is E cell is equal to E naught cell minus 0.059 by N. Here number of electron transferred is 2 log product concentration. Here product is H plus and it is present 2 times by power 2, and here H2 it is present in gas form. Whenever gas form is present, that we have to take it in pressure form. So we take pressure of H2. Generally this H2 is having 1 atmosphere pressure in hydrogen electrode. Okay, right now we see. So whenever you take hydrogen electrode, for it standard electrode potential value can be taken as 0. Hydrogen electrode, it is a reference electrode. Its standard electrode potential value can be taken as 0, and pressure of hydrogen gas, it can be taken as 1 atmosphere in hydrogen electrode. These two values is substituted here, then we get like this. E cell is equal to here 0 minus 0.059 by 2 log H plus power 2 is present, because partial pressure of H2 can be taken as 1. Okay, these two we write here. Okay, then it can be converted like this. E cell is equal to minus 2 into 0.059 by 2 log H plus is present. Okay, right, by cancelling 2 minus 0.059 log H plus is present. Now we see here minus log of H plus. In place of this we take pH. Okay, pH, when you want to find pH, the formula is minus log of H plus. So minus log H plus plus we take pH, then it can be converted like this. E cell is equal 0.059 into pH. It is the relation if you want to find electrode potential for hydrogen electrode. Okay, if you want to find electrode potential for hydrogen electrode at oxidation, that means oxidation potential, E cell is equal to, we take 0.059 into pH. Okay, similar condition if you applied at cathode, hydrogen electrode can be act as anode as well as cathode. If you take this equation as cathode, in that case that is a reduction reaction, that potential is called reduction potential. Okay, if you want to find reduction potential, the formula is E cell. Here we take minus 0.059 into pH. Okay, it is the formula if you want to find reduction potential. Okay, so if you want to find reduction potential, it is for hydrogen electrode, E cell is equal to, we take minus 0.059 into pH. Okay, and if you want to find oxidation potential, the formula is E cell is equal 0.059 into pH. Okay, these relations we can use whenever pH values are given and asking to find electrode potentials of hydrogen electrode. Okay, so based on the condition, in the condition the reaction, in that reaction hydrogen can be act as a cathode or anode, we can see. Based on that we can take the formulas. Okay, right now, and last one, if you want to find solubility product, okay, for example, we take AgX, it can be present as Ag plus X minus. Okay, for this reaction if you want to find solubility product, E cell is equal to E naught cell minus 0.059. Here 1 electron can be transferred, Ag plus X minus means 1, and log product, here product is Ag plus X minus by reactant. Reactant can be taken as AgX. Okay. Right. You see, at equilibrium condition, this you applied at equilibrium condition. So at equilibrium, E cell value can be taken as 0. By taking this we write that side. So E naught cell. E naught cell is equal, this minus we write whenever that side can be converted into plus 0.059 log. Here you see product Ag plus product of cation and anion, it can be taken as solubility product, that is Kas. Okay. By using this relation, we can find electrode potential whenever solubility product is given. Okay. Or solubility is given, by using solubility product and solubility relations, we can get Ksp values. By substituting Ksp value, here you get electrode potential values. Okay. So these are some relations based on Nernst equation. From these relations, we have to get some questions. So compulsory, we can practice this. Okay. Overall, Nernst equation is E is equal to E naught minus 0.059 by N log product concentration by reactant concentration. Okay. In this equation, N indicate number of electron transferred. How many electrons are transferred in the reaction? By substituting that, we get E cell value and E naught cell. Okay. E naught cell, it is standard condition, and E cell, it is normal condition. If the reaction is at equilibrium, E cell value can be taken as 0. Okay.